Good evening, everybody. Thank you for taking the time from your busy days to join me in this presentation. A few points of order. Thank you very much for the introduction. I'm presenting this through the company Count Zero Limited, my own consultancy company. The slides are all unencumbered by IP. It's all my IP and my copyright, and therefore you are free to reuse it as you see fit. The only restriction being it would be nice if you commented that it came from me. Right, so here we have, you may be more or less familiar with high frequency trading, HFT, and low latency trading and the various issues. I will cover those briefly, and then I'll look at some optimization case studies around them. I'll look at some examples in these optimization case studies, primarily the effect of the compiler, with various quirks and static branch prediction or switch statements. And then we've all heard C++ can be used for templating, for extreme optimization. Then I put it all together and look at this thing called a fixed to MIT bit translator. Do not be worried about these acronyms. I will explain them in due course. And then we'll have a look at other compilers, because I mainly look at GCC, but I've also looked at a bit of Clang. And then I'm going to have a look and take a bit of a holistic approach. What's the impact of the operating system and hardware on performance? And I'll look at this in terms of the results of this fixed to MIT bits translator. Then we'll come to a conclusion. Now, I've been told questions should be reserved to the end, so I shall try to keep this to 45 minutes and leaving the remaining time for questions. So, HFT and low latency trading. What are they? The idea is you've got some trader somewhere who creates a computer program that wants to model a trading algorithm or strategy, and then that program runs to place trades. The key point here is they're clever and they create an intelligent strategy. Then what happens is they want to make it fast, because the faster you are, the more edge you get, the better the market you get, and therefore you make more money. So, it's also not rocket science. It's not safety critical. Remember mentioning I worked in the nuclear industry. It's not airplanes, rockets, or reactors. And perversely, to be truly fast is to do nothing at all. Nothing runs faster than zero code. The problem is it doesn't do an awful lot. Another key point about the systems I work on is basically we've got the algorithms generating trades, messages, and they need to be copied to the exchange. And then the exchange sends messages back and they need to be copied back. So it's basically message passing with a bit of validation, perhaps risk checks and so forth. Because we look at very high performance here, it requires low-level control of the hardware and software, which interact intimately. And also, we want to tune assembly perhaps from the C++ statements. So if we look at the hardware, we want to look at things like multiple processors. We might dedicate one processor for the operating system, the other one for our trading system, so that interrupts on the processor for the operating system won't distract from the trading system running quickly and rapidly and smoothly. We might have multiple buses per processor and various cores dedicated on the second processor to certain tasks called pinning. We might be considered a network infrastructure, for example, co-location, where we rent a rack space from the exchange so we can put our computer in there so it's physically close to the exchange so the speed of light is mitigated. And of course, there may be bugs. Software issues obviously confound us. Which operating system? Not all distributions are created equal, as you will discover. Toolset support. Remember, to create software, if software is to run fast, it needs to be delivered to run fast. And if it takes ages to deliver that software, Morgan Stanley may have beaten me. Internet may have beaten me. Also, as I mentioned, configuration like C groups, ISOL CPU, and various performance tuning ideas. As I mentioned, not all compilers, as we will discover, or even versions were created equal. Which is faster, Clang, GCC, or ICC? I'm mainly going to focus on GCC, mainly on C++17, but I will also present a few results from Clang and ICC. Be warned, there will be some assembler in here. Okay, this is an AMD bulldozer, which actually I happen to have behind me, and circa 2013. It's a bit old, but it's quite hard to find these diagrams for modern processors because they're usually fairly secret. The key points here, in fact, the whole thing is a key point, but amongst the key points is we can see at the top leftish, the L1 instruction cache. This is where our instructions come from main memory, and we want to ensure a nice flow of instructions into there so we don't have pipeline stalls. We want the right mix of instructions so all our decoders can run rapidly and without stalling, and we can fill them all. Our dispatch wants to be kept full. We want to make sure that we have a good distribution of register usage so that then when we come down to our integer clusters, we don't really use the floating point unit, so we'll ignore that. When we come to the integer clusters, our ALUs and so forth are all nicely full of those instructions that's been fetched. But they're operating, of course, as you can see, that little pink corner, the L1 data cache, that's really important. We want to keep our data hot in the cache. So the design of our code is carefully crafted to make sure that this all works in a simpatico manner. I mentioned bugs, and we've heard of Spectre and Meltdown and the effects that these can have. The point being that what happens with speculative execution is that you can leak data about what's occurring from one process to another process. And the mitigations were produced, but the point is these mitigations effectively turned off out of order execution. They turned your superscalar processor into a RISC processor. But that's only for the kernel context switches. Billions of devices were affected in Intel and AMD architectures, and the mitigation via kernel patches is critical to avoid these attacks. Now, these also, as I will explain, do impact and should impact the use of even systems that are co-located with exchanges. So we can see I've chosen to use C++ because I can optimize it heavily, as you will see. And I'm going to look at the influence of the compiler, operating system, and hardware, as I mentioned. Optimizing it is not trivial. I'm going to look at some performance quirks in compiler versions as a warm-up, and then static branch prediction, its use and abuse. Switch statements, can they be optimized? And extreme templating, the case of memcopy. Remember, I said that a lot of this is just message passing, copying from the input socket to the output socket, with some bit fiddling going on in between. And then we'll put it all together. So here we go. Performance quirks in compiler versions. They normally improve with versions, shouldn't they? Here we have a simple, very simple piece of code. Here I have a string, and I want to copy it to its destination. Static, so it's internal to the translation unit. So that means that we don't have to worry about global descriptor tables, etc. And we've got memcopy. And I've statically sized this so that size off is a constant. It should appear in the iCache. What do I ideally expect when I have the .text section? I expect the .text section to be generated with the source string in the destination string. There should be no opcodes run. This is obvious. This can be optimized at compile time. Is it? Well, if we look at early versions of GCC, 447 and 473, we can see the assembly generated. This assembler was generated via Matt Godbolt's website. If you look up Godbolt on your favorite search engine, you'll find it. Now, what we can see here is various instructions. These move abseek. In fact, when I said the floating point unit, this is actually for the vector unit. And I'm trying to make use of the vector unit to maximize the performance. So here we can see that that string has been encoded as immediates in that move abseek. So we've got immediates in our code, and there's our destination. Okay, it's not actually generated at compile time, but this looks pretty good. I'm not touching the data cache. Data cache is slower than registers. Data cache is slower than immediates from the iCache, And as you saw, the iCache is 64K versus 16K for my data cache. So I'm saving valuable space in that data cache for stuff that really needs it. But then we look at GCC 473 and what's happened? Look, source has been generated. So what's happening is the source will have to be pulled in from main memory into the data cache and then into the registers. It's much slower. Moreover, we see it doesn't use any SSE instructions. There was clearly an issue between GCC 447 and 473 in terms of optimizing this code. If we look at more recent versions of GCC, coming up to GCC version 10, we can see, again, 4.8 to 6.3. It flips back to using the iCache and encoding the string as an immediate. And then we look at GCC 7. It's gone back to using the data cache again and using the stack. And then we look at GCC 8 and to 10. Likewise. So we can see the problem is as well is if I'm optimizing my code, the optimized code is very unstable according to the compiler version I use. So it may run faster in one version and then I use a different version and it might run slower or faster. It all depends. This is a serious problem. Okay, ICC and Clang. ICC is created by Intel. Surely Intel, with their vast knowledge of processors, etc., would know many things about this. But we can see likewise ICC and Clang all suffer from the same problem of using the stack. But also we can see that Clang has very stable output. So although the performance may not be great in terms of this micro benchmark, we can see that it will be very stable with different versions. Does it matter in reality? Here's my GNU plot for you. The issue here is we can see, if we look at the various benchmarks I've got on the x-axis and performance on the y-axis, and note that's a log scale, we can see massive variation in performance here. Higher is better in terms of performance. And we can see all the various versions of compiler here. And we can see this gives us direct insight into the very issues I was talking about. The actual benchmarks themselves are to do with small strings and small string optimization. So we can see here, we've got small string, construct and destroy it, a big string, construct and destroy it, small string assignment, big string assignment, small string replace, big string replace. And we can see that different compilers are affected differently by different code. Okay, static branch prediction, use and abuse. Which comes first if I have an if bar 1 or the else bar 2? Which is statically predicted if this branch has never been seen before? There's a lot of talk about this and it's quite hard to discover the details, and there's references there for you, but basically the BT-FNT rule should be used. Backward taken for loops, forward taken is an if then else. Intel added operand prefixes, but they're no longer used. The issue is that superscalar architectures suffer costs of misprediction, and this misprediction, remember I showed you that picture of the bulldozer chip? It causes stalls, and this breaks up our flow, and a pipeline stall can cost around 20 clock cycles. It's very expensive. We could use built-in expect to try and guide them, guide which is the fall through. To cut a long story short, the fall through should be bar 1, not bar 2. Okay, here we have my example. Very simple piece of code. Which is it? We can see these now, I've used 00 and 01. 00 and 01 are similar to each other, and we can see here with 01, we can see earlier versions of GCC do it the wrong way round. They statically predict. Sorry, 00 and 01, they do it the correct way around. They statically predict bar 1, and then bar 2 is the mispredicted. But if we look at other versions of GCC, for example, we change from 02 to 03, it flips round. Look at GCC 8.1. Look at that, bar 1 is now statically predicted. This is a serious problem because it basically means if I've optimized my code for fall throughs where, for example, I was expecting, here we see 4.8 to GCC 4.82 to 7.5 at O2 and O3, bar 2 is statically predicted, but newer versions of GCC flip it around. I actually raised a bug report about this regarding GCC. Why are they doing this? They seem to have solved this, but the problem is if I've optimized for GCC 4.8 to 7.5, I've optimized for the else. Now I change to 8.1 or 10, I've got to change all the likelies and unlikelies in my code. What about ICC and Clang? Well, ICC and Clang are both consistent. They get it the right way round. Yes, GCC reverses the order of calls, as I was saying, compared to Clang. So if I've got my code optimized for GCC and I use it for Clang, I will have sub-optimizations as far as static branch prediction is concerned. Why is static branch prediction interesting to me? The point is when I'm sending lots of orders, most of the responses are going to be order placed on the market and then it's going to be cancelled, and the order will be modified a bit to tune the price, placed back on the market. Rarely will I get an order fill, but that order fill I want to come back through as fast as possible. So I actually jimmy my static branch prediction. So I statically predict the unlikely thing to occur, the order fill, because I want that to go through faster, and I'll pay the cost of that misprediction for the cancels because they're less important to me. Does it affect us? What's the real effect? Well, the reality is that if I add likely and unlikely to my small string benchmarks that I was talking about, I can actually see it has an impact negatively. Look at these small string constructors and destructors. We can see there is a statistically significant performance difference there. If I move to newer versions, then that performance difference disappears. If we change the C++ ABI, there is no impact. Now, again, we look at the effect on newer versions of GCC, and we can see the built-in expect here for small string assignment, that's made a performance improvement. This is good. We can see the small string constructors and destructors. We had a slight performance degradation with adding it. So the problem is it's not obvious. The performance impact is not obvious when you try and jimmy the static branch predictor. You have to do it very carefully. Again, we can see likewise for GCC 7, we can see significant differences in 7.1, 7.3, both with built-in expect and otherwise. And most importantly, the result is quite unexpected. Using it caused a slowdown. Again, the similar occurs on these graphs. I will leave them for you to study in greater detail later. Right, so let's skip ahead and look at case statements. Sorry, switch statements and case labels. Common law seems to indicate that there is a case label, or the default, the first one, may somehow be statically predicted as a fall through. This is not true. There's a complex algorithm used in GCC. You can look at that later, but there's no static prediction. So again, here we have a simple example for my non-contiguous labels. And we can see that there's something complicated is happening, but basically a depth first search occurs. And there's the effect of built-in expect. What happens is that there's no effect. But Clang and later versions of GCC are affected by built-in expect. So again, we've got to be very careful which version we apply our built-in expect to in the hope that we will get better performance. Okay, we could hoist the misbehaving label and put it in an if statement or something, but remember I spoke about static branch prediction. Okay. We're in C++. How about using some template metaprogramming to optimize my mem copy so it is the fewest number of instructions using AVX, AVX2, and all of this lovely stuff, and generate perfectly designed minimal numbers of instructions, mem copies. And this is a huge amount of template metaprogramming that I've chopped out. You can see the snips here, because there's no way I could ever fit it on a slide. What we can see is, remember the mem copy I had before? What's happening here is we're always using the stack. But we can see that we've got my instructions, my AVX instructions are being issued, and also we can see that scheduling is occurring across the various versions, which is good. Clang has a very stable output, unlike GCC. So judicious use of micro-optimized templates could provide a performance enhancement. In ICC, likewise, we can see the stack is still used, and it also, like GCC, seems to have very unstable output. Does it really matter? The long, short, and middle of it is that sometimes it gets optimized out. We can see on the leftmost graph, that peak there, that's actually running so fast, it never occurred. It never happened. It was optimized out. The compiler just did the .text thing. But that was for standard mem copy. We can see that, in fact, my advanced mem copy provided no performance advantage. The reason is in fact, the architecture. The AMD Bulldozer chip has a particularly slow AVX unit and vector unit. Again, different versions of GCC show similar results. There's no real performance difference. So sometimes micro-optimizations, although they may look good, don't actually pay off in the end. Again, Clang shows various performance, despite its stability, it shows various performance differences. And there's even possibly the hint that in certain versions of Clang, Clang 7, that the micro-optimized version might run faster. And certainly in Clang, later versions of Clang on the right-hand side, there's a hint that it may run faster. If we look at this long graph, and I will have to skip this because of time, going into it in too much detail, but here we see the compiler versions on the x-axis, performance on the y-axis, where, because it's a rate, higher is better, we can see that if it's too high, you know, around that 10 to the 16 at the top, it was optimized out. This is what I want. I want it to be optimized out. No code is run. It's the compiler has at compile time figured out what I wanted to do and just done it. This is excellent. But we can see that it's very variable. It's very unreliable. Likewise, with the various other tests, this original one was for the constructor and destructor. This is for assignment. There's no real consistency also between these. So we have a great deal of difficulty. Here we have the replace. Again, difference in consistency here. It's not very reliable for GCC. Okay, now we'll move on to this. We'll put them all together into this simple fix to MIT bit translator. So what I'm going to do is I'm going to explain. Fix is the financial interchange protocol, and it's an ASCII protocol, name value pairs, and it's very slow and it's not very well designed, but it's used. MIT, BIT. BIT is Borsa Italia, the major Italian exchange, and that's the protocol it uses. It's a binary protocol. Why am I not talking about the LSE here? Because B comes before L. Simply, that's the reason, no other. I use something called Boost ASIO for my communications library. Often it's considered using third-party libraries is evil and bad. Well, my answer is, we've seen with the micro-optimizations, unless it's proven, why? Micro-optimizations, all the effort, may not be worth it. So unless it's proven otherwise, I'm going to use Boost ASIO. I could have used hardware. Remember I mentioned about networking. I could have used funky cards like SolarFlare and Open On-Load drivers, which are high-performance network cards, and they would have reduced context switches. Remember I mentioned about Spectre and Meltdown and the potential performance impact. They should have been greater mitigated with these, but I don't have a SolarFlare card, so I can't test that. So what we do is we create this new order message in a program. We send it to my translator. It translates it to the native binary format, sends it to a simulator that I've written. It sends back a fill, and then that's translated back to a fixed message, and the client receives it. And that's the time. That's my wall clock time. And I repeat this gazillions of times to make sure that I get a good average for in case, you know, there's something's happened on my computer, that there was a context switch occurred or what have you. I tried it with both quiet and busy computers, when I was surfing the web, etc., or leaving it alone, with and without NUMA control for pinning. I've used Gentoo Linux, so I have a highly optimized kernel. And I do have 2 physical processors. Remember, I was saying assign processor 0 to the operating system. Processor 1 is assigned to our translator. This is what I did. But it's of a vintage, 2013, over 7 years old. In fact, my computer's probably about 8 to 9 years old. So really quite creaking. My laptop isn't. We'll come to that. Okay, so we mentioned Boost. Is a library any good? And here we have a graph. I wrote a very thin wrapper I call glibc that simulates what Boost ASIO does, but without all the error handling and all of that. I created a histogram. This is for, as you can see, look, number of samples, that's about 10 to the 7, 10 million orders. So the statistics here are very good. And we can see quite clearly, using ASIO or glibc, there is no statistical difference between the two. You might squint and think that glibc is a bit moved to the left, that peak. The reality is look at the standard deviations, look at the means. Really, you'd be lying to yourself, honestly, if you thought the glibc one was faster. So, okay. We don't need to worry about the network in there and the way I'm handling the network. So let's look. Remember I mentioned about compiler versions and how they impact performance. Again, we've got a performance here at the graph. Apologies here. Higher is slower. This is the time it takes to do that round trip of send a new order, translate it, send it to the simulator. Simulator sends back a fill, translates that, receives it at the client. That's my time for sending the order. And we can see that the magenta line lower, that's the time for the simulator to run. The turquoise line above, that's the time for the whole round trip. We can see older versions of GCC on the left, newer versions of GCC on the right. It's very variable. We can see there's a spike here around GCC 6.3 of a serious performance loss. We can see that past GCC 7, we've got a performance degradation, which is regained at about GCC 8, but it's still not as fast as it used to be. And off to the far right, we can see we've got Clang here, that step up towards the right. Clang generates code that's about as slow as GCC 7. Sometimes it gets it right, and newer versions of Clang are about the same speed, generate code that runs about as fast as GCC does. I also tested the idea of what about RDTSC versus CPU ID, RDTSC and RDTSCP to measure times. These are clock instructions on my computer, because if I'm creating the histogram, recall the slide earlier, I'm measuring the time for each order. Does measuring time have an impact on the performance? Well, let's have a look. Here we're using Boost ASIO here, and what we've got is the same test case, but with one I'm using the in order RDTSC instructions, or I'm using out of order RDTSC instructions. And we can see there's various heartbeat messages, the new order, the response, and then some other heartbeats that are delayed. And we can see that there is a subtle difference. What we can see is the out of order looks, if you squint a bit, that the peak looks broader and it looks slightly faster. Well, this would be true because it's a superscalar architecture. Whereas the in order, as it means, it's meant to be in order in the superscalar chip, the peaks look tighter and they look a little narrower. And this is precisely what we would expect. But most importantly, look at that mean, 14 microseconds. There's no difference in performance. It doesn't matter. It does not affect the processor, whether we use the in order or out of order, but the in order will give us a slightly more accurate histogram and a slightly more accurate measure. Okay, now remember I mentioned about pinning. Remember I said we've got processor 0 and processor 1. And I want to make sure my software runs on processor 1. So what I've done is I pinned it. And here we can see the difference with using in order and out of order when I'm pinned. And we can see again a similar effect. The in order appears to give sharper, narrower peaks than the out of order, which fools us into looking a smidge faster. It isn't actually. There's the mean is 14. So we can see that clearly the in order technique for timing, taking time, A, doesn't impact our performance, and B, gives us, for the histograms, a more accurate result. Okay, I was talking about pinning and I was talking about my processors and so forth. So here they are, LS Topo. And we can see on the left, we've got 2 processors and we've got 6 cores each. And what I did is I used the right-hand processor, node 1, and units 6 to 11. And what I did is I pinned each thread to a certain core, and I also set the priorities for them and so forth. What impact does this have? Well. Here we see the green is pinned, magenta is unpinned. Clearly pinning, our mean has changed from 14 microseconds to 13 microseconds. Our standard deviation with pinning actually got broader, interestingly. Whereas with no pinning, it didn't. It was sharper, but we get better performance. Well, statistics of a normal distribution can be highly misleading because remember, this is not a normal distribution. I can't have negative latencies. It must be some kind of Poisson distribution because it doesn't go negative. So to use standard deviations for this can be very misleading. Also, the Q factor, the standard deviation reduced with pinning. So our statistics got poorer. Interesting. Now, remember I was saying that it's all well and good creating this fast software, but how long does it take to create it? So I looked at how long does it take to actually compile my code. And it's very variable. We can see these slower compilations on the left are GCC. The faster compilations on the right are Clang. But we can see that GCC 9 on my Ryzen 9 laptop and Clang on my Ryzen 9 laptop, much faster. So clearly using a faster computer has a big impact. But still, we can see GCC to compile the same code is significantly slower, 4 to 8 times slower than Clang. Getting Clang to compile was, getting my code to compile on Clang was a bit of an issue. You'll forgive me, because of time, I'm going to skip these. You'll be getting all the slides, so you'll be able to look at this later. Okay, what about the operating system? We've got many operating systems. The city tends to use for HFT, it tends to use a variant of Linux, generally CentOS, because they don't like to pay for Red Hat. They use it an awful lot, CentOS. I used an ISO image not tuned. I then used Ubuntu. And then I used all the results you've seen are from Gentoo. The hardware I used was another computer, an overclocked Haswell. Didn't apply any firmware patches to the processor with regards to Spectre and Meltdown. I was assured by Intel that Skylakes aren't so heavily tuned to HFT, so therefore Haswell, using the Haswell was reasonable. Intel were interested in these results when I looked at Spectre and Meltdown. Again, I didn't use SolarFlare fancy network cards like SolarFlare. What's the impact of the operating system? Well. If we look across this, we can see on the x-axis different operating systems, and on the y-axis is my mean round trip in microseconds. So higher is slower. And we can see that CentOS clearly lags behind Ubuntu. And then on the far right, we can see Gentoo obviously is the fastest. You can see error bars on these. All of my error bars are mean average deviation, because remember I was saying that standard deviation, we're not using normal distribution, so standard deviation is an inappropriate measure, in my opinion. So I use mean average deviation, and the deviation is down to around 2%. And these will run literally millions of times. Clearly, the impact of the operating system is very significant and not to be underestimated. Okay, what about hardware? We can see my old AMD, fairly slow. It's a slow system. Then we can see the Intel Core i7, pretty fast. And now I've got a laptop I'm presenting to you from, which is a brand new laptop with a Ryzen 9 3900 running at 4.3 gigahertz. And my, is it fast. And then I had, for a bit of fun, I had to go on a Raspberry Pi, one of these. How fast is that? Well, obviously it's slower, because come on, a Raspberry Pi at 1.5 gigahertz, you know, give it a break. And it's an ARM chip, give it a break. But crikey, look at it. It's coming in at 250 microseconds. This is well less than a millisecond. It really is quite remarkably fast. And it's running Raspbian, untuned Raspbian. Very, very interesting. Okay, what about the impact of hardware bugs? Remember I mentioned about Spectre and Meltdown and so forth. Well, we can see pre and post mitigations, CentOS has quite a serious impact on the earlier versions of CentOS. The later versions of CentOS, the impact is less significant. What about Ubuntu? There are many variants of Ubuntu I tried, but what the chief point is here is that we can see there is considerable variation before and after. The after is always slower by a significant amount. So therefore, the impact of Spectre and Meltdown mitigations should not be ignored. And on Gentoo, what's the impact? Likewise, there is also an impact on Gentoo, as we can see here. So it is not to be ignored. So, in summary, we have a very complicated situation. We've got me trying to tweak the software. How much performance benefit do I get? Well, recall those graphs. We roughly doubled our performance. But the problem is we've got to keep profiling, which takes a lot of time. And we've also got to make sure we don't accidentally break things. Because if we're busy tuning our code, we're removing instructions. Removing instructions means potentially removing a feature. We're trying to do the same thing in a smarter way, but we might make a mistake, so we've got to keep testing. Remember, time to ship is important as well. So if I'm too busy testing because I broke something with a micro-optimization that only gave me 5%, maybe I should just buy a faster chip. Yeah. You saw the difference in performance between an old AMD versus a relatively old Haswell that's about 4 years old versus a brand new up-to-date Ryzen. It's very hand-tuned code, as we can see, is very sensitive to versions of the compiler and operating system. And we can see that choosing the right compiler is incredibly hard, and that we may, if we change the compiler, have to re-optimize. We end up becoming locked into the compiler because of what we're doing is we're making implicit use of its instruction sequence that it generates. Another big problem is newer versions of GCC 7 and 8 are actually slower than GCC 6. Don't tell your boss, because all those shiny new features in GCC you won't get, because they'll want to stick with the older compiler that just works. Clang has stable performance, but the problem is its performance of generated code is potentially slower than GCC 7 and 8. And the choice of the operating system can have an equivalent impact to the choice of the compiler to the choice of the hardware. The effort spent on massaging code, pardon me, effort spent on massaging code that's wrong. No, the effort spent on massaging code is significantly greater. And the effect of massaged code is significantly smaller than the impact of the compiler or operating system. Don't micro-optimize your code, choose a better compiler. Choose a better operating system. And you know what? I just ran these off the ISOs downloaded, right? It doesn't take long to boot off an ISO image. So it's in terms of bang for buck and effort, as a micro-optimizer, this point really disappoints me. That my effort spent in massaging the code has a significantly smaller impact than the compiler or operating system choice. We need to select our hardware first and OS very wisely. And sadly, no one compiler appears best. Choice of that compiler is absolutely crucial for your for the system that you wish to run on it. Because remember, these micro benchmarks, they reveal some indicators that there could be a difference in performance. I rolled it all together into the translator, and we saw that some of those performance differences that were negative were actually pessimizations, came out and worked very nicely. Those AVX instructions issued by my optimized mem copy on the Haswell, and particularly my Ryzen processor, which have spectacularly fast vector units, that really came into its own. So you might find a micro-optimization you've introduced and looked a bit, didn't seem to have much impact. Changing the hardware, suddenly it can come into its own. Conversely, the opposite may occur. You have to profile and profile again. And of course, remember Amdahl's law. I am presuming, of course, you've already run your val grind, Kakash grind, your performance profiler. So you've already massaged your code so that the 10% of the code is taking 90% of the time. There's no point doing any of this until you have already optimized your code with all the standard tools available. Never attempt to guess, because you can see the problem is with, say, for example, static branch prediction. GCC will do its best to confound your micro-optimizations there. So you have to plan ahead very carefully and consistently test. Also, you've got to make sure you're testing on the same operating system as that used in production. Because if I'm doing performance testing on my my desktop or my dev machine under my desk at work, and then it's released to production, which is an older processor with an older operating system commonly, well, that performance could be very different. My SLAs could be broken. Sadly, this is the times we live in. Mitigations for Haswell had a high impact on CentOS, over 12%. Ubuntu, over 5% performance loss. It's extremely important to verify these performance impacts. And also, for example, you may need to look at other things, not just your system. Your system might include the networking in between. So you might have firewalls, etc., that might need mitigations. People might claim, but this is internal. Remember, I've got a trader who's generating who's got an algorithm that's running that's generating orders. This is in a fix message, which is an ASCII messages, which are handled in ASCII buffers. And we've all heard of ASCII buffer overruns of ASCII messages, haven't we? And in this case, Xubuntu is 8% faster than CentOS. And may I say, I am so pleased that Red Hat have decided to can CentOS. CentOso est delenda, I say. CentOS must be destroyed. Also, how do we demonstrate to the regulator that our mitigations we have taken with regards to Spectre and Meltdown are acceptable? Regulations require software audits that demonstrate that clients can't access each other's data. The point is that because I'm handling these ASCII messages, we could have buffer overruns, so we could get leakage of information via Spectre and Meltdown. So if I'm running a trading system and somebody else is running some other program, they could potentially obtain order information, private information, which is in breach of the FCA regulations. Well, as I was mentioning before, discard Amdahl's law at your peril. Obviously, choose your optimization strategies very carefully. Never underestimate the choice of the operating system. The law is that the operating system takes about 4%. I do hope that these slides have done at least one thing, absolutely fundamentally shaken that law out of your mind. The operating system has a great impact on the performance of HFT, performance sensitive code. And it may not be just HFT code. Optimizing one's own code is not necessarily a panacea, as you can see. And third-party libraries, remember I mentioned Boostazio, this is other people doing your work for you. It's a great idea because they've done all that testing. They've made sure it works over the compilers. They've made sure it works on the operating systems, and you don't have to worry. And with that, I come to an end. Thank you very much, ladies and gentlemen, for listening. You've been very kind, and I look forward to any questions you may have.
Excellent, Jason. Thank you very much indeed for a very thought-provoking talk. I don't pretend to have understood all of it. And if I were a cynic and I were to say to you, well, does all this really matter? Because all you've got to do is throw a bit more money at it, just over-specify the kit, and it'll all be fine. I mean, that's what programmers have been doing for years, isn't it?
You're absolutely correct. And in fact, that is an extremely valid conclusion to draw. And given that my laptop cost me £1,500, that performance boost, if you imagine how long it took me to get that 2 times performance improvement, very roughly, that GCC tries to steal from me and Clang tries to steal from me, as we can see in those graphs, that takes a lot more money than £1.5 grand for a Ryzen 9. So why is it that banks don't just buy a faster processor? Because they've got IT infrastructure. And they have a massive amount of drag due to they need to test all the software on it. They tend to block purchase. Because they're block purchasing, they need to test all the systems on it to make sure it works. They're carefully manipulated operating system. They may have customized CentOS, ye gods, and they need to test that on it and so forth. It takes them years to upgrade their hardware platform. So for them, in fact, perversely, although the programmers are very expensive and it's very expensive to do these micro-optimisations, that's actually the cheaper and the only avenue of flexibility that we have.
I've got a question here from Nick, who says, are there compiler flags or directives that influence the compilation of the source code, e.g. to influence static branch prediction on a global or a case-by-case basis?
There is not a global flag, no, not as far as I'm aware. And on a case-by-case basis, one can use the built-in intrinsic called built-in expect on GCC, and there may be equivalents on Microsoft compilers. I'm not familiar with that. I don't compile on Microsoft at home. I don't have Microsoft at home, so I can't comment there. I believe there is an equivalent intrinsic for Microsoft compilers, but please look it up. And as I've mentioned, the problem is that GCC does its best to confound you.
Yeah. And question from Ashok, and he's talking about the new releases of, he's talking about programming languages, and I guess he would include versions of the compiler. And he's asking that, is there no template testing process that's applied so that efficiencies gained in previous releases can be maintained in the new release?
Banks are the banks that I'm familiar with are, in some cases, they didn't have any SLAs and I added them. In other cases, they did have them, and in other cases, they didn't at all. And they didn't want them adding because they just said it's good enough, or buried their head in the sand until the traders complained. So no, there is no standard template for this, sadly. And you would be right that one would readily imagine that, in the dev room for the HFT programmers, there's a kind of monitor sitting there that instead of showing Bloomberg, useless Bloomberg news, shows instead, current performance of the system, green, amber, red, with a graph. And then you can look at it and go, oh, golly, something gone wrong. And again, with each check-in, you see, performance tests are run. The problem is the performance tests take a long time to run. Those performance tests across different operating systems took me at least 2 weeks. Now, if you're looking at a release that takes 2 weeks just to get past the performance tests, cripes.
Yeah, your work is primarily in the financial industry, but another question has come in, which is, do you think this would be applicable to other industries? So, for example, clean energy production, distribution usage, self-driving cars, the space industry?
Absolutely, totally. There's nothing about what the code I have written that is somehow, yes, it might be relating to the finance industry, but there is nothing special about that industry at all. You're absolutely correct. And that the results I have given, to some extent, it's like a mathematical proof. If there exists an example where it means that it admits the fact that there must be others as well, or can be others as well. So therefore, I have demonstrated using, I happen to have used HFT and this MIT fixed to MIT bit translator, which is for the finance industry. But that's an example that demonstrates the case that precisely compiler, version, operating system, hardware, etc., the impacts of those, they could, if you write something for, say, I don't know, games programming, the same will affect you. If you write something for rocket industry, the same will affect you, precisely. Because remember, I've covered different processors. It might be x86. Oh no, I covered ARM as well. So I didn't even cover only x86. So clearly, yes, absolutely correct.
And a question about the different compiler versions. I think the name is Seamal who's asked this on YouTube. He's saying that trading applications obviously contain thousands of lines of code. So how can you decide which is the faster for the whole system, given the complexity of the system?
Ah, yes. How do you narrow down on those 10 lines of code that are burning the extra 5% of performance and to tweak it? Well, as I mentioned at the top of this slide, it says discard Amdahl's law at your peril, right? What I first do is I run, say, I happen to like to use Valgrind with KickHashGrind as a front end to view it. It gives them nice tiles, and then you can see there's the big tiles, and you can drill down into which functions are taking the time. You can optimize those, and then what happens is it ends up becoming lots and lots of tiles of equal area, and then it takes suck it and see. You end up putting in your time counters. That's why I was talking about the cost of measuring time. You put your RDTSC instructions, your in order instructions in there. And what you do is you move them around the code to see which bit in that code path looks like it's taking the majority of the time. And then you essentially bisect your code until you find those hot lines, as it were.
If any of our audience want to follow up on this and they're new to high efficiency, low latency, what resources and sources do you recommend to them to get started?
Well, I have to admit, I kind of learned it on the job. So I didn't really refer. Nowadays, there are quite a few blog posts, books, and papers written, but you've got to remember it takes time to write those and publish, etc. So you're always, if you're reading those, you're going to be behind the curve. But it also means that you've got a good foundation to build on. amongst those are, I hope, my slides, and which will be published via BCS Hertfordshire, and also a lot of my publications, my slides are on ResearchGate as well, where you can look, and there are other people as well and their experiences.
Yes, the slides are up on hearts.bcs.org as we speak. I'm mindful of the time. I'd like to say thank you to you, Jason, and to all our viewers for their questions. Before we go, do you have your clock handy? Because I'm sure
I do indeed.
Our viewers would like to see it.
Oh yes, of course.
If you could perhaps talk us through it.
This is a clock. It was sent to me as a kit. I had to assemble it. Laser Mad is the name. Don't work for them. And what it is these are vacuum tubes. So they're actually olden vacuum tubes. They come from the Ukraine, and they're about 30 years old. The clock shows time, but I added a GPS chip to it, a GNSS chip, so it can take satellite data from Baidu, GPS, GLONASS, etc., Galileo when it works sometimes, to show GPS time. And then I added, remember I mentioned the Raspberry Pi? Well, here is a baby Raspberry Pi, a Pi 0W, and that's running my NTP server. So now in my home network, I can connect to I can use NTP on my laptop as a client, and it can prefer this as the NTP server for its preferred time. Excellent. I have arguably the world's, and indeed I even have the benefit of being able to VNC into my clock.
And I can confirm that it keeps perfect time because we're heading towards 8 o'clock, which is our normal stopping off point. So many thanks again, Jason, for a very illuminating talk, and to all our viewers who've submitted questions. I'm sorry if we didn't have time to get through them all. If you've enjoyed this evening, please make sure that you push the like button and let us know your thoughts in the comments. If you haven't already, please subscribe to our channel and hit the notification bell to be informed about new Hertfordshire content, and look out for more videos coming soon. Our next event is another collaborative event, this time with BCS Ethics Group, and that's taking place on Tuesday the 30th of March. Our speaker is Dr. Blay Whitby from the University of Sussex, and his topic is Life in the Age of Artificial Intelligence, Job Losses, Regulation and Policies. So, on behalf of everyone here at BCS Hertfordshire, have a very good evening, safe journey home, I don't need to say, and good night from us. Good night.